Hello everyone, thank you for watching this video on the weekend. I hope that you're doing well and had some time to relax. So today we're going to begin a new topic about factoring. So it's our next chapter, chapter 6. But before we do, I'd like to just begin as usual with some reminders about some things you've got coming up this week. So on tomorrow night, so Monday, you've got written homework 5 due, which is on chapter 5. So as always, that can be found on Blackboard. Chapter 5 was about expanding and multiplying and adding and subtracting polynomials. And then Tuesday night, you've got 2 My Math Labs due. So those are the last 2 sections in chapter 5. And then Wednesday, we've got quiz number 4 due. So this will be the same as always. This will open on Tuesday after class at 10:50. And then you can start it at any time on Tuesday or Wednesday, as long as you complete it by midnight on Wednesday and submit it. And I think I've given you 2 hours to do that. And then, so it only covers chapter 5. So as usual, your written homework, which is on the same chapter, should prepare you well for that. And then the chapter that we're going to start this week, all on factoring polynomials, we should get through a decent chunk of it today. And then we're going to look at some applications when we meet again on Tuesday. And we should finish that up early this week. So your homework on this chapter right now will be due on Friday. So you can get started on that, when you can. We might need to move that to a later date, but I'll keep you informed as the week goes on. So chapter 6 is essentially the opposite of chapter 5. So we're going to go backwards. Instead of multiplying out polynomials, we're going to basically kind of divide them, not really divide them, but write them as a product instead of taking a product and expanding it outward. Right, so the word that we use for that is factor. So I just want to remind you what factor means. So for numbers, right, so to factor a number, it means to write it as a product. So to factor a number means to write it as a product. So for example, if you have the number 6, one way to write that as a product would be 2 times 3. And so writing 6 as 2 times 3 would be factoring it. And there are multiple ways you can factor a single number. We looked at prime factorizations, which is breaking down into just the products of things with primes. And so in this case, we do have a prime factorization of 6, and we call 2 and 3 the factors. So this also applies, or the same idea is also true for polynomials. Remember, so polynomials are just powers of x that are added and subtracted together, and maybe they have some number in the front of each of those terms. Remember, those numbers are called coefficients. So polynomials are just a word that means any kind of thing that has that form. So for example, if we were to write x to the 5th as x squared times x cubed, this is one way to factor it. Right, and I hope you remember, I know it's hard maybe to think about going backwards like this, but certainly going forwards this way, we have our exponent properties, which tell us that we have the same base, different exponents, so you'll add those together and you would get 5 as your new exponent. Right, so we could say that x squared and x cubed here are factors of x to the 5th. Right, we're not going to really factor things like this. Maybe a little bit, but our goal will be to factor more complicated things. So here's another example of something like that. If we look at x plus 2 times x plus 3. So we talked about how to multiply out binomials like this, right? It's essentially foiling, or basically that means distributing each of the terms, right? So the x into the x and the x into the 3 would give us x squared plus 3x. And then we distribute the 2 into the x and the 3, and so that would give us plus 2x plus 6. Or in other words, x squared, combining like terms together, gives us a 5x here plus 6. Right, so the polynomial over here could be reversely factored and written as x plus 2 times x plus 3. And so we're going to spend today talking about how to do that. So again, this x plus 2 and this x plus 3 here, we would say are factors of x squared plus 5x plus 6. Okay, so main idea here is that factoring is essentially the opposite process of multiplying or expanding out. Now we're going to go through a lot of different like factoring techniques. In the end, I'll give you a summary, kind of like a roadmap of how you know like what kind of technique to use, but it really comes down to practicing. So again, you have you know, my math lab's due on all of this, and you have the written homework. So I hope that you take the time to practice when you're not told exactly like what kind of technique to use. But we're going to go through them one at a time. So the goal will always be to write our product like completely factored, so where we can't factor the products anymore. So essentially like prime. The first and easiest method that you want to try when you're trying to factor something is to factor out a greatest common factor. So factoring out a greatest common factor will apply to anything that we look at, whereas some of the methods that we will look at later will only apply to certain like forms of things. So GCF factoring applies to anything. Right, so GCF means greatest common factor. So just as a reminder of what the GCF is, let's take a look at these few lists I've got here and find the greatest common factor of all of the terms in the list. So first example, 20 and 30. So the greatest number that goes into both 20 and 30, or the greatest thing that is a factor of both 20 and 30. I mean, that's going to be, I mean, we could list all of our factors here, but sometimes you can kind of like reason through it. So, right, 10 goes into both 20 and 30. The only largest thing larger than 10 that goes into 20 would be 20, but that doesn't go into 30, right? So 10 will be the greatest common factor here. All right, 40 and 100. Okay, so it's not going to be 40. Remember, it can be one of the numbers themselves. It's not going to be 40. The next biggest thing that, for example, goes into 40 would be 20. And that also does go into 100. So that's got to be the greatest common factor here. So 20. A lot of this just comes down to some number sense. 7, 21, and 28. Okay, so again, I mean, if you look at the smallest number that can kind of help you, so the biggest thing that goes into the smallest number here, which in this case is 7 itself. And if you look at 21, that is 7 times 3, and 28 is 7 times 4. So 7 goes into all of these 3 numbers here, so the greatest common factor here would be 7. All right, when you've got variables involved as well, the only extra thing you have to do, so you still have to look at the numbers, but the only extra thing that you've got to do is look at the variables. And the greatest common factor with the variables will just be the lowest exponent in all of the terms that you've got. So for example, in number 4 here, you've got 5x and x to the 5th. So the numbers here, or the coefficients, are 5 and 1. And so looking at those separately, the greatest common factor would be a 1, right? And then you've got x to the first and x to the fifth. And the greatest factor that goes into both of those powers of x would just be x to the first. So the greatest common factor of these two terms here is going to be just x to the first. All right, example number 5, we've got 12x cubed and negative 15x to the second. So go ahead and, you can always, this is pre-recorded, so you can pause this and work this out on your own or go ahead of me. As always, I encourage you to do that. But you want to look at the numbers separately, 12 and the negative 15. Think, what is the largest number that goes into both? I think our number that we're looking for here is 3. So that's going to be part of our greatest common factor. We normally don't pull out the negative as part of the greatest common factor unless both of the terms are negative. So since only one of the terms here is negative, we're just going to pull out just the 3. And then we've got x cubed and x squared in our variable parts. Right, so the biggest exponent on the x that's common to both is the second power. So we'll have 3x squared as our greatest common factor. All right, so right now we're not factoring anything out, we're just finding the greatest common factor. In just a second, we'll actually factor out the greatest common factor in each of the polynomials. Okay, lastly, here's just an example where you've got multiple different variables, but the same process applies. So you're just going to look at the numbers separately, find the greatest common factor of each of those, look at the variables separately. So here we have x and y, and we'll find the greatest exponent that can be taken out of each of the x and the y powers. So looking at the negative 11 and the 33 and the 55, right, our smallest number here is 11, and luckily that does go into 33 and 55, right? So the greatest number factor that we can take out here will just be 11. And again, one of them is negative and these are positive here. So I would just take out the positive 11 rather than the negative with the GCF. Then looking at our powers of x, we've got x to the fourth, x cubed, and x squared. And so the largest power that is common to all of those is going to be the x squared. Right, we can't go higher than that because in this last piece here, we don't have any more x's to take out. Then looking at the y's, we've got y cubed, y to the fifth, and y to the first. And so the largest power that's common to all those is just y to the first. So here we'll have 11x squared y as our greatest common factor. All right, so again, this is just a reminder of what greatest common factor means. Let's move on now to looking at some polynomials and factoring them just one step by taking out the greatest common factor. So the way to do this is to just look at all of the terms in your polynomial and then think of them as being in a list, like in the examples we just looked at, and find the greatest common factor of those things. So for example, in number 1, we've got 5x squared and 25. And so you want to think of what is the greatest common factor that you can of those two things. So use the same method as before. So you look at the numbers first. So we've got 5 and we've got 25. Right, the largest number that goes into both of those is going to be, let me write this down here, is going to be 5, right? And then you look at the powers of x. So here we've got x squared. Here we don't have any x, so there's no x in common here. So the greatest common factor is just 5. So when we factor, we write this as the greatest common factor, and then we have to see what's left when we factor it out. Now, since factoring is like the opposite of multiplication, really what we're looking for is what we get when we divide all of the terms by the greatest common factor. Right, so dividing 5x squared by 5 will just give us 1x squared. And then we still have plus, and then dividing 25 by 5 will give us 5. And so there we go, we factored out the greatest common factor here. And we can always check. by multiplying out again. Right, so if we distribute the 5 back, oops, I wrote that wrong there, right? That should be plus 5. So if we distribute the 5 into both the x squared and the 25, we get 5x squared. Sorry, I said 25 again. 5 times the 5 will give us 25 here. And so we got back to where we started from. And so we did a good job. All right, example number 2, we've got x squared minus 10x. Okay, so again, we look at the numbers. So we've got really a 1 in front of the x squared. We've got a negative 10 in front of the x. So the greatest thing that can go into both of those is just a 1. Then you look at the powers of x. We've got x squared and we've got x to the first. The greatest power that can go into both of those will just be x to the first. So our greatest common factor is x to the first. So now we actually want to factor this. So we're going to take out the x. And remember, factor means write as a product. So I need to see what's left over when we divide all of the terms by the GCF. Okay, so in here we have x squared divided by x. So that'll give us x to the first. Then we have minus 10x divided by x. And so that just gives us 10. And so there we go. We've factored out the greatest common factor. All right, example number 3, we've got 9xy squared plus 3x squared y. All right, so GCF equals, okay, look at the numbers. We've got 9 and 3. Okay, so the greatest common factor of those numbers is 3. Then we've got x to the first and x squared. The highest power that is common to both of those will just be x to the first. Then we've got y squared and y to the first. And so y to the first is the largest power that can come out of both of those pieces. So our GCF here will be 3xy. All right, so now we want to write this as a product. So I'm going to take out the 3xy greatest common factor. And I want to see what's left over when I do that. So that's the same as dividing all of the terms. Here we've just got 2 by 3xy. Okay, so here on the first piece, the x's cancel. Let's see, the 9 over 3 gives us just 3. The x divided by x gives us 1. And the y squared divided by y gives us y to the first. So that'll just be 3y. You see where all of our exponent rules and all the things that we've been working on have, are building here, right? The y squared over y, same base dividing. So this would be y to the 2 minus 1, which is y to the first. All right, in the second piece here, we will have plus. And then here we've got 3 divided by 3. So those divide to give you 1. We've got x squared over x, so that divides to give you just x. And we've got y over y, and so those divide to give you just 1. And so that second piece is just an x left over. And so there we go. We have written this as a product by factoring out the greatest common factor. And again, I'm not checking these, but we can, right? And you should do that as you're working. All right, example number 4, we've got negative 4x squared plus 16x minus 20. So here we've got 3 terms. We have negative 4x squared, we've got 16x, and we've got negative 20. And it's really up to you whether or not you want to take out the negative number in this case. I know before I said that we don't usually include the negative sign in the greatest common factor. However, when we're using these polynomials to work with them to do something, and the leading coefficient, right, this is the leading term, the highest degree here. I'm trying to highlight it, but it's not showing. Oh no, my thing is frozen again. Why does it do this to me? All right, hold please. Got to reshare my screen here. Are we back? Okay, yeah. So here we go. So I'm trying to show you this, right? This leading term here has got a negative in the front. And when that's the case, it's usually harder to work with. So you do want to, in fact, take out that negative if the leading coefficient here is negative. So, I mean, we look at our three terms. We look at the numbers. We've got -4, 16, and -20. And finding the GCF of those numbers, okay, well, think about the smallest number here really is the 4. So the biggest thing we could possibly take out would be 4. We want to check, does 4 go into 16 and 20? Yeah, I think so, right? So the GCF here we're going to take out is going to be a -4. And then you look at the variable parts. So here we've got x squared, x to the first, and there's no x here. So we can't take out any x's. All right, so we're going to divide every term by -4. And then it doesn't just go away, right? We're writing as a product, and so we take out the GCF and we multiply what's left over by it. It doesn't just disappear. Okay, so -4x squared divided by -4 just gives you x squared. We've got plus 16x divided by -4. So that'll turn into minus 4x. Then we've got -20 over -4, and so that'll give us plus 5. And so there we go. And when you're doing this with the GCF, whatever you get left over, it should not have any other factors in common with the terms. Otherwise, you did not take out the greatest common factor in your first step, right? So like if we look back up even to example 2, right, the x and the -10, they've got nothing in common for us to take out. Right here, the 3y and the plus x, they've got nothing in common for us to take out. So we did a good job with finding the greatest common factor here. Okay, example number 5, we have got 8x to the 5th plus 10x to the 4th minus 7x cubed. All right, so look at the numbers, 8, 10, and 7. 7 is the smallest. That does not go into 8 and 10, and 7 doesn't have any other factors. It's prime, right? So there's not going to be any numbers we could take out. But the variable parts, the x to the powers here, we can take out a highest degree of x cubed. Okay, so let's see what will be left over when we divide each piece here by x cubed. So let's see, we're writing this as x cubed times, all right, in this first piece, we've got 8x to the 5th over x cubed, so we'll still have an 8. X to the 5th over x cubed, we subtract the exponents, so we'll get x squared. All right, 10x to the 4th over x cubed will be 10x to the 1st. -7x cubed over x cubed, that'll just be -7, right? X cubed over x cubed cancels to give you 1. And there we go. All right, number 6, we've got lots of m's and lots of n's here. Different powers, 4 different terms. Not really any numbers in the front except ones and -1s. So we won't need to worry about the numbers here. We need to carefully look at the powers for the greatest common factor. Okay, so definitely some m and some n powers in the greatest common factor because they're present in all of the terms. So we want to look carefully at each of the exponents. So here we've got m cubed, here we've got m cubed, here we've got m to the 4th, and here we've got m to the 6th. Right, so the highest power that's present in all the terms is really the lowest power that's present, right? And so that's m to the 3rd power. Okay, then we've got, let's look at the n's. We've got n to the 4th, n to the 2nd, n to the 3rd, and n to the 8th. And so the highest power that's present in all of those will be n squared. So that's the greatest thing we can take out of every term here. So now we're going to think about dividing every term by m cubed n squared, divided by m cubed n squared, divided by m cubed n squared, divided by m cubed n squared. Okay, so I think I'm going to need some extra space here, so let's move that over. So this whole thing will be equal to, okay, our GCF was m cubed n squared. So now let's go through and see what's left over. So in this first term here, the m cubes divide to give you 1, and then we subtract the powers on the end. So this will be n to the second power. All right, the second term here, we're going to have plus. Then we've got m cubed over m cubed, so those cancel. We've got n squared over n squared, so those cancel. But be careful here, we don't get 0 because we are not adding and subtracting the same thing. We're dividing by the same thing. So this just gives you a big 1. It's supposed to be plus 1. Okay, then we've got minus. All right, in this term here, we've got m to the 4th over m cubed, so that just gives you m to the 1st. We've got n cubed over n squared, and so that gives you n to the 1st. So this will be minus m times n. And then lastly, we've got this term here. This m's will give us m to the 3rd, and here we'll get n to the 6th. Right? 8 minus 2 is 6, yeah. So minus m cubed n to the 6th. There we go. We factored that. All right, example number 7. Okay, we've got 3 terms here. Let's look at the numbers first. We've got 15, 18, and 27. I think all of those are divisible by 3, and that's the greatest number we can pull out. So GCF will have a 3 in it. Okay, then we've got XY, YZ, and XZ. There's 3 different letters here, and it doesn't look like any one of those is present in all 3 of the terms. And so I think we're just done with the greatest common factor being 3. So let's divide each of the terms by 3 and see what we get. All right, 15xy divided by 3 will give us 5xy. We'll have minus 18 divided by 3 is 6yz. And then 27 divided by 3 is 9, so we'll have minus 9xz. And that is it. Sometimes the greatest common factor is just a number, and that's okay. Okay, last example here, we've got 36a squared minus 24a times b minus 16a. Okay, so let's look at the numbers. We've got 36, 24, and 16. All right, the smallest number here is 16. Let's just check, does that go into 24? No, because 2 16s would be 32. All right, so let's think about what numbers might go into 16. I think it's easiest to focus on the smallest number. So 8 would be the next biggest number to go into 16. 8 does go into 24. 8 does not go into 36, right? We can get to 32, but not to 36. Okay, so let's look back here. So I think 4 would be the next biggest thing that could go into 16. So 4 does go into 24, and it does go into 36. So GCF will have a 4 in it. Okay, then look at the variables. We've got a squared, a to the 1st, and a to the 1st. So we can take out an a. And then only this term has the b in it, so it's definitely not a common factor. And so it looks like 4a is our greatest common factor for all 3 terms. So let's divide everything by 4a to see what's left. Okay, so we're going to write this as 4a times. Okay, the first term, 36 over 4 is 9. A squared over a is a to the 1st. Okay, we'll have minus 24 over 4 is 6. A over a is 1. B over, well, the a's canceled with the a on top, so we just have a b left. And then minus 16a over 4a, so it'll be minus just 4. And so there we go. All right, now this greatest common factor factoring technique is going to be a really, as we go through all of our factoring techniques, it'll be the one we want to always start with. So these are going to build on top of each other. And as you are just looking at something to factor, the first thing that you want to always keep in mind is you're gonna wanna be paranoid to see if there's a greatest common factor that you could take out, because it could make the rest of your factoring a lot easier if you do that first. So yeah, so let's move on to a couple harder examples here. I forgot I had these. So here we go. Still greatest common factor. But these are a little bit different. So sometimes the greatest common factor is not a monomial, right? If you look back over here, 5, 1x, 3xy, negative 4, x cubed, m cubed, n squared, 3, 4a. These are all single term things. Sometimes the greatest common factor can be a binomial or a trinomial or any term nomial. So you just need to look where the things are separated by the plus. All right, so here we've got two pieces. We've got this piece and this piece. And the thing that's common to both of those pieces is the x plus 1. Right, and that's totally okay for your GCF to be something like that. Okay, so we can factor that out here. So what this is going to look like is x plus 1, but we need to keep it in parentheses. And we're still going to divide to see what's left over when we take out an x plus 1. So they'll cancel there, they'll cancel here. And what we'll be left with is x squared plus 2. Okay, so this blue plus will stay basically here, and then you just get what was in front of each of the, what didn't cancel out when you divided by the x plus 1. Okay, so go ahead and, maybe you can just see looking at the rest of these what the GCF is. So you can pause here and try to figure these out on your own, or leave it going and check up with me as you work. So same thing here, but now we've got minus. But if you notice in this piece and this piece, the same a plus b part occurs. So the GCF here will be a plus b. Okay, so we can factor out a plus b by dividing each term by a plus b. So here we multiplied by a plus b, so we're dividing by it, so it goes away, or it divides to 1. Here we're multiplying 5 by a plus b, so that'll go away too. And so when we factor, this will be written as a plus b. And then what we'll have left is the x squared in front of this first piece here. We still have this blue minus, and then what we have left is a 5 with the second piece. All right, example number 11. We've got 3 times 2x plus y minus z times 2x plus y. Okay, and so I hope you can see here, right, the greatest common factor will be 2x plus y. I didn't really mention it before, but if we're looking at the 3 and the z, there's nothing more you could take out, right? If here we looked at the x squared and the 5, there's nothing more we could take out. At the x squared and the 2 here, there's nothing in common with those either. It was just the other part with the parentheses. Okay, so let's see what we've got left when we take out the 2x plus y. Let me just move this over here. So this will be, all right, so we're going to take out the 2x plus y. So we're dividing both terms by 2x plus y. Okay, so here we've got 3 times 2x plus y divided by 2x plus y, so it's like we did nothing. The z times 2x plus y divided by 2x plus y, we can just cancel those out and get 1. And so what we're left with, this minus here, we've got 3 and then minus z when we factor out the 2x plus y. So that'll look like 3 minus z. And there we go. Right, lastly, we've got 7p squared times 4p minus 5, and then minus 4p minus 5. Right, so maybe you can see here, again, we're looking, so here by the things separated by plus and minus. So we've got this chunk of stuff, minus this chunk of stuff. Right, and the thing that's common to both of these is the 4p minus 5 that's being multiplied here. And really there's a 1 here, so we're multiplying here as well. Okay, so the GCF here will be 4p minus 5. Okay, so when we factor this, right, we're going to write this as 4p minus 5 times something. All right, so to find out what that something is, as always, we're going to divide every term by 4p minus 5. Okay, so in this first term here, the 4p minus 5 goes away here as well. And so in the first term, we will have 7p squared, right, then minus. And then what's in front of the 4p minus 5 here is really a 1. So don't forget that. It doesn't just disappear. We need to include this 1 here. It's really important. Okay, and so there we go. We have factored out the greatest common factor. All right, so like I said before, once the greatest common factor has been taken out, we're going to want to check to see if what's left can be factored further. And so the GCF will be our first kind of like thing to look for, but what's left over could be could need a number of techniques. So we've got, I think, 1, 2, 3, maybe 4 kind of categories to look at after that. And so the next thing is factoring by grouping. And the way to recognize when this will work is that it sometimes, not always, but it sometimes works with polynomials that have 4 terms. So if you see something that's got 4 terms, then you might try factoring by grouping. So for example, number 1 here is xy plus 2x plus 3y plus 6. Okay, so 4 terms, right? We've got term 1, term 2, term 3, term 4. So what the factoring by grouping says is it says to group into 2 groups of 2. And then look for the GCF of each of those groups. So in the first group, the xy and the 2x, the greatest common factor that we could take out is an x to the first. In the second group, the GCF of the 3y and the 6, the greatest common factor is a 3. Okay, now factor out the GCF of each of those. Okay, so this will be x. And in the first group, we will have a y plus 2. Okay, then we've got plus. Here we have a GCF of 3 that we'll factor out in the second group. And we are left with a y plus 2 when we factor 3 out of the second group there. All right, so all I'm doing is this group is equivalent to the first group that we had underlined in the blue, and then here as well. Okay, and then if you're lucky, if this works, what you have got in the parentheses should be the same in both of the terms separated by the overall plus or the overall minus here. So then, just like in the examples we just looked at, the GCF of this and this is y plus 2. And so then we can factor out a GCF of y plus 2. And what we're left with here is the x and then plus 3. And there we go. There we have factored by grouping. All right, let's try example number 2. We've got x cubed plus x squared plus 2x plus 2. So 4 terms. So to see if factoring by grouping will work, we're going to look at the GCF of each of the 2 groups. So here GCF is x squared. And here GCF is 2. Okay, so then you want to actually factor out those GCFs. So here, if I take out an x squared, I'll be left with x plus 1. And here, if I take out a 2, I'll be also left with x plus 1. Right, so again, here's that same stuff, just factored. And now we got lucky again, right? The x plus 1 is the same in each of those terms or each of those pieces here. So I could take out an x plus 1. Right, and what we are left with, so again, here's the GCF of the first one, here's the GCF of the second, here's the overall plus, and so what we are left with when we take that out would be an x squared, and then plus the 2. And there we go, we have completely factored that by grouping. All right, you can try number 3 on your own if you'd like. I'm going to move on to example number 4 here. So let's look at, so we got 4 terms here, so let's try factoring by grouping. So here are our 2 groups. All right, group number 1, the GCF, I could take out a 2 and a z to the second. In group number 2 here, in the second group, okay, you've got a negative 3, z, and then minus 3. So you, in this case, we should take out a negative 3. Okay, so what we've got left then when we take out the GCF of 2z squared in the first group, right, what that will look like is z to the first and then plus 1. Okay, and then we're going to take out a minus 3 in the second group. So it'll be all of this. And what we've got left when we take out a negative 3 from the negative 3z will just be positive z. And then the negative 3, again, we're thinking of this as dividing by the negative 3. So negative 3 over negative 3 would give us positive 1. Okay, and then again, we've got overall in this piece here, the way it's written, we've got a big GCF of z plus 1, so we can take that out. Then we've got 2z squared and then minus 3 left. And so there we go. We have, again, factored by grouping. All right, we've got a few more here. I'm going to skip number 5. You can try that on your own if you'd like. I'll do number 6 here. So this one is 5xy minus 2x minus 5y plus 2. Okay, so 4 terms. So again, group into 2 groups of 2 and find the GCF of each. So here we could take out an x. And in the second group, can't take out really anything, just a 1. But when this first term here is a negative, you want to always get rid of that and make it a plus, because then the terms that you'll get when, you know, let me say here, like this piece and this piece, you don't want them to have different signs. So always take out, if this sign here is a negative, like it is here, try to get rid of that by taking out a minus with the GCF. Okay, so here let's take out a negative 1. All right, so what we've got left here then is x times 5y minus 2. And just here's that first group. Then we're going to take out negative 1. Okay, when we do that with the 5y, we'll just have 5y. And now plus 2 divided by negative 1 gives us negative 2. Right, and so maybe you can see here like why we needed the negative 1, because otherwise this would be minus and this would be plus, and that wouldn't match with this over here. Okay, so 5y minus 2 can come out, and then we are left with x minus 1. All right, I'm going to skip example 7. You can try that on your own if you'd like. Let's look at number 8. We've got 4 terms here, so try factoring by grouping. Here are our 2 groups. GCF here looks like to be a 4 and then x. GCF in our second group looks like it is a 2 and then y. Okay, so let's factor those out. Let's see, in the first group, when I take out a 4x, we've got a 4x left over and then plus y squared. Okay, when we take out a 2y from the second group here, it looks like what we will have left over is a 4x and then plus a y squared. We've been getting really lucky with these. Sometimes it just doesn't work this way. I mean, I've been giving you ones where it does work. However, if you get to this point and these two are not the same, then you've got to try a different method. Okay, so what have we got here? Now we can take out the 4x plus y squared. And what we have got left is 4x and then plus 2y. And there we go. And I broke something that I told you that we should do. I told you that we should always look to see first if we could take out a GCF of everything. And I didn't look. I haven't been looking. But we could 16, 4, 8, and 2. We could have taken out a 2 to begin with. And then we would have gotten kind of, this would be divided by 2. We'd have a 2 out in the front, and then 2x plus y here. But in the future, we'll definitely do that.